Hey, what's up? It's your old pal, Mr. Cook. We're going to go through the rest of this Unit 7, Part 2 test review. So we went through the first 14 problems. Now we're going to go through, I don't know, let's see. We'll do 15 in this one, 16. If that, find the series expression from that. Yeah, we'll do through 17 in this. And then the last three we'll just do in one video. So in a previous video, we went through number 14, which is the first problem for interval of convergence. And I went into that one with a little bit more detail than I'm going to do in this one. So what I want you to do, and what I'm going to do is go through this kind of fast just to show you that it doesn't take a long time to get these ones done. So first, when it says interval of convergence, unless it's a geometric series, which this is not, then you just write out, use the ratio test on it. So limit as n goes to infinity, absolute value of the interval. And then, so you use the original sequence, this one, in the denominator, -1 to the n plus 1, then x minus 4 to the power of n over n times 9 to the power of n. And then you do that same exact sequence, but wherever you see an n plus 1, okay? So you'd have -1 to the power of n plus 1 plus 1. Then you'd have x minus 4 to the power of n plus 1. And then you'd have, see how we have an n right there? That's going to turn into n plus 1. And then instead of 9 to the n, it's going to be 9 to the n plus 1. And then from here, we just simplify it. So if I am dividing by a fraction, it's the same as multiplying by the reciprocal. So this turns into -1 to the n plus, let's simplify this a little bit. N plus 1 is going to be n plus 2. And then it'll be x minus 4 to the n plus 1 over n plus 1 times 9 to the n plus 1. And then times the reciprocal of the denominator. So I'd have an n in the top, 9 to the n in the top, and then the bottom would be, that other stuff, -1 to the n plus 1, and x minus 4 to the power of n. Okay, and then from here we just simplify. So looks like I've got, let's see, what are some things I can simplify? If I have x minus 4 to the n plus 1 here and x minus 4 to the n, I can take out n many of the x minus 4s. So for the first thing that I would eliminate or simplify down is that x minus 4. And I'd only have one of those left over, and it'd be in the numerator. All right, and then let's see here. If I have 9 to the n and 9 to the n plus 1, I can take out 9 to the n many terms from there, but I still am left with 9 to the first. So in the denominator, I've got a 9 to the first, or just 9. And then I can't really do anything with this n plus 1 or n, so I'm going to leave those there. N plus 1. And then the other cool thing about this is whenever you've got -1 to any power, it doesn't really matter. This absolute value here is just going to cancel those out. So just ignore those ones. They get eliminated by the absolute value. Okay, so that's what it simplifies down to, which is pretty easy. Now remember that the limit is only working with the n's. So anything with an n in it, like n and n plus 1, I'm going to keep in there, in the limit. But everything else I'm just going to kind of move out and multiply out or factor it out. So I'll have an absolute value of x minus 4 over 9, and then times the limit as n goes to infinity of the rest of it. So that'd be absolute value of n over n plus 1. And yeah, and you're allowed to do that again because the x value is just a number, so you can factor out any constant numbers that are multiplying on some function or sequence of n. Okay, and then the next thing that we're going to do is, use this limit. So this is a simple rational function. Since the degree in the top, which is 1, and the degree in the bottom, which is 1, they're the same. We just compare the coefficients, which would just be 1 in this case. So this turns into absolute value of x minus 4 over 9, and then times 1. And multiplying by 1 just, it doesn't do anything. So I can just kind of ignore the times 1 there. Okay, so that's what this limit turns into. And remember that this is convergent if the limit, convergent. So it converges if this limit that we get, absolute value of x minus 4 over 9, is less than 1. Okay, that's where it'll converge. That's really good. So what we're going to do is just figure out what the x value is to figure out our interval of convergence. And then we just have a few more little steps that we got to do. And then it's pretty easy from there. Okay, so let's see here. It looks like since I have a 9 in the denominator, this absolute value isn't going to affect it. So I'm just going to keep the 9 kind of out of it like that. Okay. In other words, I can just kind of like bring a 1/9 out front if I wanted to, like that. Because, 9 is never going to turn negative. It'll just be itself, so I can pull that out. Then if I multiply both sides, if I multiply that, that 1 by 9, then I would end up with the following. Absolute value of x minus 4 is less than 9, okay? And then I can remove the absolute value by just surrounding the x minus 4 with, 9 and negative 9, okay? So this is like a trick that you can use with absolute values because this will be true, this statement will be true if this turns into 9 or if it turns into negative 9, like at the limits, right at the edges. So there we go. That's our interval of convergence so far. And then we just got to add 4 to both sides to get x. So if I add 4 to this side, negative 9 plus 4 is going to give me a negative 5. And if I add 4 on this side, 9 plus 4 is 13. So as long as x is between negative 5 and 13, this thing is going to converge. But I also got to check and see if, that also happens at negative 5 and 13, like if it converges there. So here's the logic behind it. It could converge if this limit that we have, 1 over 9, absolute value of x minus 4, is equal to 1, okay? Because remember, when we did ratio test, it was inconclusive at 1. So here's our opportunity to check to see if it works, if it's inconclusive. So this is what you need to do with intervals of convergence. In number 14, it went from infinity to negative infinity, so we didn't really know what happened at the end. But this one, since it's like regular endpoint values of negative 5 and 13, we got to check and see what happens at those locations. So here's how we do it. Let me get a different color here. Let's use black here. So I'm going to check what happens when x is actually equal to one of these endpoints, negative 5. So I'll go back to my original series, that's this. And what I do is I plug in negative 5 and I see if it converges or if it diverges, okay? So let's see, I've got negative 1 to the power of n plus 1, and then x minus 4 to the power of n over n times 9 to the n. I'm kind of doing that one off memory, so I should probably check to make sure that that's correct. Negative 1 n plus 1, x minus 4 to n, and 9 to the n. There we go, good. All right, so what we're going to do is we're going to plug in negative 5 to this, so plug it in for x, and we're going to see if this converges or not. If it does, cool. Then that means that we will be able to add a little equal sign here because it also converges at that endpoint, negative 5. Otherwise, we'll just leave it like this. So let's see what happens. So if I plug in negative 5, here's what I get. I got to do a little bit of algebra on this one. So negative 1 to the n plus 1. Then negative 5 minus 4 is going to be negative 9 to the n over n, and then 9 to the n. I can simplify the heck out of this thing because check this out. Negative 9 to the n is actually the same thing as saying negative 1 to the n times 9 to the n. So that's what I'm going to rewrite this as, okay? So if I just, after plugging that number in, now if I simplify this a little bit, I get negative 1 to the n plus 1, and then negative 1 to the n, and 9 to the n, all over n times 9 to the n. Do you guys see something that's going to cancel out the top and the bottom? Yeah, you got it. It's that 9 to the n. So I'll be able to simplify that a little bit. There we go. That's gone. And then check this out. This is also really interesting. So whenever you've got two exponents multiplying, if they have the exact same base but different exponent powers, do you remember what you do with that? If they have the same base, you combine them into one exponent and the exponent powers add together. So that's what I'm actually going to use. I'm going to use that rule with this stuff here, okay? Because they have the same base, negative 1. So if I rewrite it, it looks something like this. Negative 1 to the power of n plus 1 plus n, all over n. Well, n plus 1 plus n gives me 2n plus 1. And here's the deal. No matter what n value that I plug in here, I'm going to end up with an odd number every single time. Try it. You plug in 0. 0 times 2 is 0. 0 plus 1 is 1. If you plug in, say, like 1, 1 times 2 is 2. 2 plus 1 is 3. So 3. You keep getting odd powers. And anytime that you take -1 and raise it to an odd power, it's always, always, always going to be -1 every single time. So that means that I can actually rewrite this so that it looks like this. N equals 0 to infinity of just -1 over n. And that's it. That's, what this simplifies down to. So can you tell what this is right off the bat? Remember back in the first part of Unit 7, we learned all these ways to tell if things are convergent or divergent. This thing is a p-series. That's right. So if it's a p-series, if my, p-value is equal to 1, right, because I can move that negative out front if I want to. See, now it's a little more clearly a p-series. If n is equal to 1, this thing is going to diverge. So that means that it's going to diverge. And you know what this ends up doing to our interval? Instead of adding a little equal sign on here saying that it also converges at -5 when x is equal to -5, I'm just not going to put that on here, okay? Now I do the same thing for 13, and I see what happens. So I'll use a different color for when I use 13. Let's use green. So if I use x equals 13 here, okay, in the same exact sequence, I just plug it in over here instead. So 13 now. I'm going to see what happens with this thing. If it converges, I'm going to add a little equal sign on there for my interval. If it doesn't converge, I'm just not going to add it in there. Okay, so let's see what happens. So if I plug in 13, right, 13 minus 4 is 9. So I end up with n equals 0 to infinity, -1 to the n plus 1. And then 9 to the n, I'll just write it as 9 to the n, over n times 9 to the n. Do you guys see something that cancels in the top and the bottom? Yeah, the 9 to the n. Good, good. So that cancels out. And now I've got this thing. So this is an alternating series. And alternating series test is the best thing for this one. So if I use alternating series test for this one, I need 2 rules. Okay, so the first one is I got to make sure that the limit of the sequence goes to 0. In the sequence, I just ignore the alternating part. It's just going to be 1 over n. And sure enough, as n gets substantially large, this does go to 0. So that's a check. That part works. All right, the next thing is that I need to make sure that this sequence, decreases. So what I would do is I would just either graph out 1 over n, which looks like this. And yeah, sure enough, as n gets really, really big, this thing is going down and to the right. So this will decrease. So that'll work, show the graph. Or I can show the derivative. And if I take the derivative of 1 over n, that ends up being -1 over n squared. And yeah, sure enough, no matter how big n gets, it's still going to be a negative number. So that's going to be true, no matter what n value that I use there. Or the last thing is I can use an inequality. And this is probably the one that I would use. And I would just show that 1 over n is actually going to be bigger than 1 over n plus 1. And that makes sense, right? Because if the denominator in a fraction is bigger, then overall you're going to get a smaller number. So this is true also. All right, so since both of these things are true, that means that this is going to be convergent. And watch what I do. I just add a little equal sign on here. So this is going to be my interval of convergence. And if you're more of a fan of interval notation, you can just write it like this. X, as long as it's in this interval starting at -5, going all the way up to 13, but including 13. That's another way to write it out. Okay. So either way is fine, using an inequality, so this one, or using interval notation. But as long as you get that, that interval correct, you're going to be all right. Okay, so there we go. That's the first problem, number 15, right? Yeah, 15. And that was a doozy just because it came out to a result that took a long time. This one looks like it's going to be a lot faster. So let's see what we do. So again, we use ratio test for this one if we have to find the interval of convergence. So ratio test. So we take the limit as n goes to infinity of, it's a big fraction, right? We put the original sequence in the denominator, so -1 to the n plus 1. And then x minus 1 to the power of n plus 1, all over n plus 1. And then we add 1 to all the n values. So that becomes -1 to the n plus 2 now. And then x minus 1 to the n plus 2. And then it's going to be all over n plus 2. Okay, and let's skip some steps here because the -1 to the n in either case will get absorbed by this absolute value. So I'm just going to skip that step and just rewrite it with that part gone. And then also with multiplying by the reciprocal of the denominator. So I end up with x minus 1 to the n plus 2 over n plus 2 times the reciprocal of the denominator, the quantity n plus 1 over x minus 1 to the n plus 1 power. Okay, and then a lot of stuff simplifies here as well. I can get rid of like n plus 1 many of these x minus 1s. So that leaves me with only 1 left over here. So I just have like a lone x minus 1 in the numerator. And then I can't really do anything with these n plus 1s and n plus 2s. So I'm just going to leave them as is. N plus 1 and then n plus 2. Okay, well, again, I've said it a few times. Since this x has nothing to do with n, I'm just going to like kind of factor it out. Okay, so here's what I get. I get the absolute value of x minus 1. Then that's going to be multiplied by the limit as n goes to infinity of n plus 1 over n plus 2. And just like before, as as n gets really, really big, this is just a rational function, and the degree in the top is equal to the degree in the bottom. So that just is going to turn into 1. So this is absolute value of x minus 1 times 1. Okay, now to make this thing convergent, I need to make sure that it'll converges at, when the absolute value of x minus 1 is less than 1. So, I'd get rid of the absolute value there. So I get negative 1 is less than x minus 1, which is less than 1. Then add 1 to both sides. So I know that x has to be less than 2 and it needs to be greater than 0. Okay, but we're not done there, obviously, right? Because we need to see what happens at the endpoint. So I'm talking about what happens at 0 and what happens at 2. So that's when we need to take our specific x values, plug it into the original sequence, and then solve that series, see if it converges or not. So let's start off with 0. So let's let x equal 0. And then my original sequence was, there it is. Okay, so n equals 0 to infinity of negative 1 to the n plus 1, x minus 1 to the n plus 1, all over n plus 1. So if I plug in 0, there we go, a little 0 right there. Well, 0 minus 1 is just going to be negative 1. So that means that I've got n equals 0 to infinity of negative 1 to the n plus 1 times negative 1 to the n plus 1 all over n plus 1. Well, I'm just going to use that same rule, because if I add these two together, right, or I multiply these two together, I add the exponents, then this is what I'm going to get. I'm going to get n plus 1 plus n plus 1. And if I add those together, that'll give me 2 n's and a 2. So 2n plus 2. And check it out. This is always going to be an even number, no matter what I plug in. If I plug in 0, I get 2. If I plug in 1, I get 4. If I plug in 2, I get 6. If I plug in 3, I get 8. Always an even number. So that means that if I take negative 1 and raise it to an even number, no matter what the even number is, this is just going to become 1. So even though I have 2n plus 2, right, it's really an even number. So since negative 1 is raised to an even number every time, it just becomes a 1. So that's just a 1, basically, over n plus 1. Okay, and now we got to see if this thing converges. And it doesn't look like it, but this is a limit comparison test with a p-series, okay? So limit comparison test with a p-series. And the p-series that I'm going to, compare this with is the one that looks like this, n equals 0 to infinity of 1 over n. And I know what happens to that thing. Since p is equal to 1, this is going to diverge. So that means that I'm pretty confident that the other one's going to diverge as well. So using limit comparison test, if the limit as n goes to infinity of, the fraction of, one of them over the other gets to something other than, well, if it goes to some constant that's like less than, what is it? It's like just something greater than 0 and some constant, it'll just basically be the same. It'll have the same outcome. Okay, so I'm going to take my 1 over n plus 1, and I guess I'll put that in the denominator or whatever. So 1 over n plus 1. And then the one that I'm comparing it to, 1 over n, is going to go in the numerator. And yeah, if it's dividing by a fraction, it's the same as multiplying by the reciprocal. So limit as n goes to infinity of 1 over n times n plus 1 over n, over 1, I'm sorry. And then I can turn that into one big fraction, n plus 1 over n. And we know what's going to happen here, don't we? Yeah, so like, the degree in the top is the same as the degree in the bottom, so that means that we just end up with a constant number of 1. And just to kind of verify, so I was a little bit shaky on that one, with the limit comparison test, as long as it comes out to some value that is greater than 0, both will converge or both will diverge, right? So it needs to be an actual value that it goes to. And sure enough, this one goes to 1. So that means that both will diverge, okay? So both diverge. So that means that this thing diverges for this value. So on our little inequality, instead of putting a little equal sign there, since it diverges, we just leave it alone for 0, okay? Then for 2, let's see what happens with 2. So let's let x equal 2 now with our little sequence that we had. So 2 is going to go in here instead. And 2 minus 1 is 1, so we end up with the following sequence: n equals 0 to infinity, and then it'll be negative 1 to the n plus 1, and then 1 to the power of n plus 1, all over n plus 1. Well, 1 to the power of n plus 1, no matter what n you plug in, is going to be 1. So we can just kind of get rid of that. It's just going to be times 1. And now this is an alternating series, so let's take a look at the alternating series test and see if it converges or diverges. So it needs to follow 2 criteria. The first one, we need to make sure that the original sequence just goes to 0. So the limit as n goes to infinity of 1 over n plus 1. Yeah, sure enough, as n gets really, really big, that does go to 0. So check. The second thing also needs to be true, and that is that it's going to be decreasing. So if we have 1 over n plus 1, then if we increase it a little bit, add 1 onto the n value, so that'd be 1 over n plus 2. Sure enough, that's a larger denominator, so that's going to be a smaller number. So that also checks out. So that means that this thing is going to converge, and we can add a little equal sign on there. So this is our interval of convergence, but we can also write it like this. X is going to be in 0 to 2, and it'll be including 2, but not including 0. So either way works. All right, I think I'm going to stop this video just because I am I think I've gone on a little bit long for this one. So yeah, I hope this helped out. And if it didn't, go find your calc teacher, get some help from them. I'm Mr. Cook. If you need help in the morning or after school, I'm available. Just come find me and I'll help you out. Okay, hope the video was helpful. See you in the next one. Bye-bye.